Hello, we will start by reviewing basic proof technique. Review of basic proof techniques. First, remember that a statement is a sentence that has a true or false value, and an implication is a statement of the type if P then Q, where P and Q are two given statements. As an example, let me give you an example of a sentence which is not a statement. Cats are cute is a sentence which is not a statement. It is an opinion, right? The fact that cats are cute depends on who you talk to. And an example of a sentence which is, let's say, an implication would be the following. If a function is differentiable, then it is a continuous function. This is a statement. In fact, it is a true statement. And the first part of the statement, if a function is differentiable, is called the hypothesis. This is your P here. And the second part of the statement, it's a continuous function, is the conclusion of the statement. All right, next, I would like to talk about the one approach of proving implications. You know, in mathematics, a lot of our the statements that we deal with come in form of implication. For example, if a function is differentiable, then it is continuous, right? That's an implication. And how do you prove that an implication is true? Well, we have a variety of techniques at our disposal. One of the tools that we have is called a direct proof. So what is a direct proof? In order to prove an implication of the type if P then Q by a direct proof, we assume that the hypothesis P holds, and we use that fact to derive that the conclusion Q holds also. So the structure of a direct proof takes the following form. You start by assume that P holds, and you use that hypothesis. This is your hypothesis. P is your hypothesis, and you use that hypothesis to derive that Q holds. So you write a variety of statements, whatever it is. This is where your creativity comes in place. This is where the work is, and then you connect the hypothesis directly to the conclusion. So in the end, you'll have something like therefore Q holds. Okay, whatever is the direct proof that you're writing, it always has this format. Okay, so let's look at a specific example. Let us suppose that I would like to prove the following. Prove directly by a direct proof that if n is an odd integer, then 4n cubed plus 2n minus 1 is also odd. Okay, so my hypothesis here is that n is an odd integer, and my conclusion is that 4n cubed plus 2n minus 1 is odd. So to approach this with the direct proof, we'll start by assuming our hypothesis. Assume that n is an odd integer, and we like to connect this assumption to our conclusion, which is 4n cubed plus 2n minus 1 is odd. Well, the fact that n is an odd integer means the following. Thus, there exists an integer L such that n is equal to 2L plus 1, and as such 4n cubed plus 2n minus 1 is equal to 4 times 2L plus 1 cube plus 2 times 2L plus 1 minus 1. And now we will expand things out. So we get 4 times 2L plus 1 becomes 2L cubed plus 3 times 2L squared times 1 plus 3 times 2L times 1 plus 4L plus 2 minus 1. And I suppose this will be, we have 8 times 4, so that'll be 32L cubed. This is, okay, this will be 4, right, times 3, that's 12. 12 times 4, that will be 48, 48L squared. 6 times 4, 24L plus 4L plus 2 minus 1, which is 1. And I'll leave the 1 there because I really want to write this as an even number plus 1. So next, then we have 32L cubed plus 48L squared plus 28L plus 1. And then I can factor 2 out of this, this group here. So we get 2 times 16L cubed plus 24L squared plus 14L plus 1. So letting let's say m be an integer such that m is equal to 16L cubed plus 24L squared plus 14L. Then we obtain that 4n cubed plus 2n minus 1 is equal to 2m plus 1. Therefore, we conclude that 4n cubed plus 2n minus 1 is an odd integer. Okay. All right. So please feel free to stop, rewind, pause, and try to digest all the various aspects of this direct proof. Okay. So let's look at another example. So for this example, I would like to prove the following. Let n be a natural number. We want to prove that if n plus 1 over n is less than 2, then n squared plus 1 over n squared is less than 4. All right, so we'll prove this directly. Again, let us assume our hypothesis. So assume that n is a natural number such that n plus its reciprocal is less than 2. Now, if you look at the conclusion is a statement about the sum of the square of n and its reciprocal. So let's try to perhaps square each side of this given inequality. So squaring each side of the inequality n plus 1 over n is less than 2 yields that n plus 1 over n squared is less than 4, and this is equivalent to n squared plus 2n times 1 over n plus 1 over n squared is less than 4, which is equivalent to n squared plus 2 plus 1 over n squared is less than 4, and this is equivalent to n squared plus 1 over n squared. Right now we want to say something about this quantity, so that's less than 4 minus 2, which is equivalent to the fact that n squared plus 1 over n squared is less than 2. So since 2 is less than 4, we obtain that n squared plus 1 over n squared is less than 4. Okay, again, we have an implication that we were trying to establish. We assume that the hypothesis holds, and using that assumption, we derive that the conclusion is also true. And this connection, making a clear connection between the hypothesis and the conclusion directly, is a direct proof strategy. All right, next we will review proof by contrapositive. So remember that the contrapositive of an implication if P then Q is the statement if not Q then not P. Also recall that an implication and its contrapositive are logically equivalent. In other words, an implication and its contrapositive have the same true value. Thus, an implication is true if and only if its contrapositive is true as well. So now remember that a proof by contrapositive is simply a direct proof of the contrapositive of the given statement. So for example, so you're given a statement of the type if P then Q, and because if P then Q and if not Q then not P have the same true value, to prove the first one, it is enough to prove the second one, and vice versa. All right. So to prove by contrapositive is to write down a direct proof of the contrapositive of the given statement. So let's consider the following exercise. Let x be an integer. We want to prove that if 5x minus 7 is even, then x must be odd. And we'd like to prove this by contrapositive. Proof by contrapositive. So let us start by assuming that the negation of our conclusion is true. So we'll start by assuming that x is even. In other words, there exists an integer k such that x is equal to 2k. Next, 5x minus 7 will then be equal to 5 times 2k minus 7, which is 10k minus 7. All right, so remember now what we want to prove is that 5x minus 7 is odd. Okay. All right, so if I take 10k, I would like to write plus 1 here, and then I need something. So what should this be here? Right? So we can, so if I need to have 1 there, in other words, let's perhaps a more straightforward way of doing this would be to start with negative 7, and then I will subtract 1 and then add 1. That way nothing has changed. So I have 10k minus 7 minus 1 plus 1. That's still 10k minus 7. But then this now here is 10k minus 8 plus 1. And then we can factor 2 out of here. So we get 5k minus 4 plus 1. And letting L be an integer such that L is equal to 5k minus 4, we obtain that 5x minus 7 is equal to 2L plus 1, which is an odd integer. So we have proved that if x is even, then 5x minus 7 must be odd. Therefore, by contrapositive, we have proved that if 5x minus 7 is even, then x must be odd. Okay, for our next exercise, we have the following. Let x be an integer. So we want to prove that if 5x minus 7 is odd, then 9x plus 2 must be even. So this is a harder proof because whether we try it directly or we try by contrapositive, we still run in the same kind of difficulty, which is it's unclear how we can use whatever hypothesis is here to derive the conclusion, right? So we'll need to proceed. We'll need a lemma, and if you go to some heuristics, you will find that whenever you try to construct an example such that 5x minus 7 is odd, you always need to select x to be even, right? So by doing a few examples, it becomes perhaps plausible that the following statement is true. So let me write it down. Lemma. Let x be an integer if 5x minus 7 is odd, then x must be even. And we'll try to prove these statements by a contrapositive. By contrapositive, let us assume that x is odd. That is, x can be written as 2k plus 1 for some integer k. Next, 5x minus 7 becomes then 5 times 2k plus 1 minus 7, which is 10k plus 5 minus 7, which is going to be 10k minus 2, which is 2 times 5k minus 1, which is even. Okay? All right. So this then established that if 5x minus 7 is odd, then x must be even. So we can now use this to try to prove the claim, the original claim directly. So let me write down the claim here again. If x is an integer and 5x minus 7 is odd, then 9x plus 2 is even. And I will now do this directly. So I will assume that x is an integer and 5x minus 7 is odd. By the previous lemma, then x is even. That is, there exists some integer L such that x is equal to 2L. Next, 9x plus 2 becomes then 9 times 2L plus 2, which is 18L plus 2, and factoring 2 out, we get 9L plus 1, which is even. So we can, let's write here. Okay, so in fact, I have therefore 9x plus 2 is even. Okay, so we established the claim by first in 2 steps. First, we use a lemma, which is some intermediate step, to prove that by contrapositive that if 5x minus 7 is odd, then x is even. And then now we can prove directly the statement, because now we have information about what it means for 5x minus 7 to be odd. It means that implies that x must be even. And using that, we get automatically that 9x plus 2 is even as well. All right, next, in proving by contradiction, if one is interested in proving an implication of the type if P then Q by contradiction, the idea here is to assume that P and its negation both hold. And remember that the negation of if P then Q is P and not Q. And also it's impossible for a statement and its negation to be both true at the same time. So to prove that if P then Q is true, it is enough to prove that its negation, which is P and not Q, is false. So again, remember, so to summarize what I just said, to prove that a statement of the type if P then Q is true, it is enough to show that the statement P and not Q is false. And this strategy, this proof strategy, is called proof by contradiction. All right, so let's get started. Suppose we want to prove that if n plus 1 squared minus 1 is even, then n must be even. Right, so the negation of this statement is the following. Remember, the negation of an implication contains no if. The negation of the statement will be there exists, let's say, a natural number here. Suppose n is a natural number. So it will be there exists a natural number n such that n plus 1 squared minus 1 is even and n is odd. So by contradiction, let us assume that there exists a natural number n such that n plus 1 squared minus 1 is even and n is odd. Okay, all right, so then thus there exists some integer k such that n is equal to 2k plus 1. And next, because this is the case, then n plus 1 squared minus 1 becomes 2k plus 1 squared minus 1, which will then be 2k plus 2 squared minus 1, which is 4k squared plus see, so this will be 2 times 2k times 2 plus 4 minus 1, which will be 4k squared plus 8k plus 3. In factoring 2 out of, I'm going to rewrite this as in fact 4k squared plus 8k plus 2 plus 1, which can then be rewritten as 2 times 2k squared plus 4k plus 1 plus 1. Okay, so Now, this is, so remember that the quantity n plus 1 squared minus 1 is even. And we have assumed that, so we have now, under our assumption, the fact that n is odd, then we have derived that n plus 1 squared minus 1 is odd. Thus n plus 1 squared minus 1 is both even and odd. And there must be something wrong with that. So let's try to make this very transparent. So in other words, there exists, let's say, integer n1 and n2 such that n plus 1 square minus 1 is equal to 2n1 and also equal to 2n2 plus 1. This implies that 2n1 minus 2n2 must be equal to 1, which means that 2 times n1 minus n2 is equal to 1, and consequently n minus 1 n sub 1 minus n sub 2 must be equal to 1/2. There are a few possibilities here. So this means if n1 is equal to n2, then this is going to be equal to 0. So either 1/2 is equal to 0, or otherwise, if n1 is not equal to n2, then 1/2 must be an integer. And both of these statements are false, since these statements are absurd, we reach a contradiction, which means that our assumption is false. It's not possible for n plus 1 square minus 1 to be even and n to be odd. So therefore, if n plus 1 square minus 1 is even, then n must be odd. Let's consider the following statement. Let n be an integer. 2n squared plus n is odd if and only if cosine of n pi over 2 is even. So remember that a statement of the type P, if and only Q, is really a biconditional statement. So it's a statement of P implies Q. It's a conjunction of the statement P implies Q and its converse. So whenever you have a biconditional statement of the type P, if and only if Q, there are two things to prove. You have to prove P implies Q, and you have to prove the converse Q implies P. The first step in my proof is to first establish that it is not possible to make 2n squared plus n odd without having n odd itself. So to do this, I will need this lemma, and to establish this lemma, which is the following: if 2n squared plus n is odd, then n must be odd. So I will proceed by contrapositive. So by contrapositive, let us assume that n is even. That is, we can write n as equal to 2k, where k is some integer or some natural number. Then 2n squared plus n will then become, very quickly going through the calculations, you get that it must be 2 times 4k squared plus k, which is an even quantity, right? So by contrapositive, our statement holds. So therefore, if 2n squared plus n is odd, then it must be the case that n is odd. All right, so this established the this lemma. Now let me come back to to the proof itself, to the original statement. Let us start by assuming. Let us assume that 2n squared plus n is odd. Then this means we already know that n must be odd. That is, n must be equal to 2k plus 1 for some integer k. So next, cosine of n pi over 2 becomes cosine of 2k plus 1 pi over 2, which is cosine of k pi plus pi over 2. Right, so remember from the unit circle, hope you remember from the unit circle, we know that so k pi will be either here or there, right? And so if I start with k pi, which is here, and I add pi over 2, I'll be there. If I start with k pi, if k is even, if it's here, and I add a pi over 2, then it's there. So in either case, the cosine of k pi plus pi over 2 is always 0. Okay, now for the other way around, because this is a biconditional statement, so I just prove that P implies Q. So for the converse, let us assume that cosine of n pi over 2 is even. Since cosine of n pi over 2 is an element of the interval -1 to 1, and since 0 is the only integer in -1 to 1, then cosine of n pi over 2 must be equal to 0. As such, then n pi over 2 must be equal to pi over 2 plus so let's think about it. So here you have the unit circle, right? And you have that you have an angle whose cosine is 0, so that angle can be either here or there. Then there are two possibilities, right? N pi over 2 can be equal to pi over 2 plus k pi. Which is then pi over 2 plus 2k pi over 2, which is then 2k pi plus pi over 2 factoring this, factoring pi out, we get 2k plus 1 pi over 2. All right, so we have found that n pi over 2 must be equal to 2k plus 1 pi over 2. So n must then be 2k plus 1 over 2 times pi times 2 over pi, and then cancelling these two out, we get 2k plus 1. Okay, so so n must be add. Next, 2n squared plus n becomes then 2 times 2k plus 1 squared plus 2k plus 1, which is going to be equal to 2 times 4k squared plus 2k plus 4k, I'm sorry, plus 1 plus 2k plus 1, and let me double check, 2 times 4k squared plus 4k plus 1, so we get 8k squared plus 8k plus 2 plus 2k plus 1, which is then 2 times 4k squared plus 4k plus 1 plus k plus 1, which is add. And this completes the proof, right? So to summarize, we had a biconditional statement: 2n squared plus n is add if and only if cosine of n pi over 2 is even. And this proof has two parts in it. There's the part where you have to prove that if 2n squared plus n is add, then cosine of n pi over 2 must be even. And you have to prove that if cosine of n pi over 2 is even, then 2n squared plus n must be add. All right. So, and for the proof, we needed a lemma because it's hard to make a statement about the parity of n if you only know the parity of 2n squared plus n, right? So, but with some heuristics, we first sort of find out that the only way to make 2n squared plus n add is to begin with n being add itself, because if n is even, then it's necessarily the case that 2n squared plus n will also be even. So the proof that lends itself well to establish this claim is a proof by contrapositive, by assuming here that this is the lemma, this is our original lemma. By assuming that n is even, it's easy to derive that 2n squared plus n must be even. All right. Once that's done, then we're able to use the assumption 2n squared plus n is add to derive that n must be add, which means that it has to be of the form 2k plus 1 for some integer k. Using that, then we can easily derive that cosine of n pi over 2 must be 0, and of course 0 is an even number. Okay, so that takes care of the p implies q part. Now, for the other way around, for the converse, for q implies p, then we start by assuming the statement cosine of n pi over 2 is even, and since that's the case, and since cosine is always a number in between -1 and 1, and since 0 is the only integer in between -1 and 1, then cosine of n pi over 2 must be equal to 0. And the fact that cosine of n pi over 2 is equal to 0 tells us that n pi over 2 has to be equal to 2k plus 1 pi over 2 for some integer. Forgot to write here, for some integer k. Solving this equation for n tells us that n must be equal to 2k plus 1, and then we derive that 2n squared plus n has to be add. All right. All right, for this second part of our video, I will talk about how to approach in general proving direct statements. So usually I always try to prove statements by directly. That's always my very first approach, and I don't usually try any other technique unless my direct proof has failed. Okay? And so if the direct proof failed, then I think about proof by contrapositive or proof by contradiction, and I'll try that as well. So let's look at other example, and I'll show you a little bit how I go through my processes when I'm writing a proof. So let me write down the claim here. The claim is the following: let x be an integer. Prove that if 2 power 2x is odd, then 2 power negative 2x is odd. So like I said, I always try to do everything directly. So let's see if we can try to establish this claim directly. So my hypothesis here is that 2 power 2x is odd. So I will say assume that x is an integer and 2 power 2x is odd. So thus there exists some integer L such that 2 power 2x is equal to 2L plus 1. Now I want to say something about the parity of the reciprocal of 2 power 2x, right? So I will take the reciprocal of this quantity here. So thus 2 power 2x inverse must be the inverse of 2L plus 1, and this means that 2 raised to negative 2x is really 1 over 2L plus 1, right? And since 2 power negative 2x is an integer, then 1 over 2L plus 1 must also be an integer, and there are only 2 possibilities. Are we taking the reciprocal of another integer to get an integer? Then 2L plus 1 is either 1 or 2L plus 1 has to be negative 1, right? Because if you're taking the reciprocal of an integer, 2L plus 1 is an integer, you're taking, I don't know, 1/3, 1/5, 1/7, and so on. You're getting rational numbers which aren't integers unless the denominator itself is 1 or negative 1. But since 2 power negative 2x must be positive, right, then 2L plus 1 has to be equal to 1. Okay, so then the fact that 2 power 2x is odd tells us automatically that 2L plus 1 must be equal to 1. As such, okay, thus there's only one way for 2L plus 1 to be equal to 1. Let's think about it. 2L must be equal to 1 minus 1, which is 0, and L must be equal to 0 over 2, which is 0. Right? So L must be equal to 0, And what does that mean? This means, therefore, the quantity 2 power negative 2x, which is 1 over 2l plus 1, must be equal to 1 over 0 plus 1, which is 1, which is clearly odd. Okay, all right, so the fact that 2 power 2x is odd implied that it has to be a number of the type 2l plus 1 where l must necessarily be 0. So the fact that that's equal to 0, that's equal to, the fact that 2 power 2x is equal to 1 implies that its reciprocal must also be 1. And we get the desired result. Claim, let x be a non-negative number if for every epsilon which is positive we have that 0 is less or equal to x, which is less than epsilon, then x must be equal to 0. Okay, and now try to prove this by contradiction. So, actually by contrapositive, I mean. So by contrapositive, suppose that x is greater or equal to 0 and somehow x is not 0. In other words, x must be strictly bigger than 0. Okay, next I will let epsilon be equal to x over 2, then clearly epsilon, which is x over 2, is less than x, right? So there exists a positive real number epsilon such that epsilon is less than x. So our hypothesis is false. Okay, so because remember that the negation of if for every epsilon greater than 0, we have 0 is less than x, which is 0 is less or equal to x, which is less than epsilon. The negation of that is that there exists some epsilon such that the inequality doesn't hold. And we have just proved that. Another exercise. Let x be a positive number. We want to prove that if x is positive, then 1 over x must also be positive. And I would like to prove this by contradiction. So by contradiction, suppose that there exists a positive number x whose inverse is not positive. Okay, so in other words, one over x is less, there exists some integer x such that 1 over x is less or equal to 0. Now, since x is positive, it follows that 1 over x times x is less than 0 times x, right? Because when you multiply an inequality by a positive number, it will preserve the inequality, and consequently, one must be less or equal to 0, violating the order structure, the ordering structure of the real numbers. Okay, all right. So this is the proof. So the claim is that square root of 2 is an irrational number. And I will prove this by contradiction. So by contradiction, let us suppose that square root of 2 is a rational number. What does that mean? This means that there exist integers p and q such that q is not 0 and square root of 2 is equal to p over q. Furthermore, let us assume that our fraction p over q is in its reduced form, that is, p and q have no common factor. Well, the fact that square root of 2 is equal to p over q implies that if you square each side, then now, okay, so now square root over 2 being equal to p over q implies that 2 must be equal to p square over q square, and this means that p square will be 2q square. Thus, p square is an even number. I claim that this implies automatically that p must also be even. So this implies that p is even. Indeed, otherwise p will be of the type 2k plus 1 for some integer k, and p square will then be 2k plus 1 square, which is 4k square plus 4k plus 1, which is add, which is clearly add. Okay, all right, so p must be even. So if p square is even, then p must be even. Okay, so so now since p is even, then p must be equal to 2l for some integer l, and this means that p square will be equal to 4l square, which is equal to 2q square, and q square must then be equal to 2l square. So q square is even, and by similar argument presented earlier, q must be even. So, in summary, P and Q are both even. This means that 2 divide P and Q, but this contradicts the assumption that the assumptions that P and Q have no common factor. All right, so we reach our contradiction. Therefore, square root of 2 cannot be rational. It is an irrational number. Okay, all right, so let's summarize very quickly. We started by assuming that square root of 2 is a rational number, which means that you can write square root of 2 as a fraction of the type p over q, where p and q are integer, and of course q, the denominator, is not 0. Now, because you can always completely reduce a fraction, so we can assume that p and q have no common factor, and this is the key of the proof, right? And now the fact that square root of 2 is equal to p over q implies that p square must be twice of q square, which then means that p square is even. And then by the argument which I presented earlier, p must be even. And the fact that p is even means that p square is of the type 4 times l square, which means that q square is even. And because q square is even, then q must be even. So if we assume that square root of 2 is a rational number in its reduced form of the type p over q, then there's only one possibility: 2 has to divide p and q. So that contradicts the fact that p and q have no common factor, so we have violated logic. So square root of 2 can never be a rational number, it must be an irrational number.